Thank you, Mark, and good morning, everybody. What I'm going to do is give a quick 5-minute introduction, sort of set the stage for three entrepreneurs who are recent entrepreneurs who will give you probably a better feel and flavor for the kinds of programs that we run. You spent the whole week, all of this week, taking a deep dive into the very comprehensive energy landscape here at Stanford. And what we'd like to do in the next 40 minutes or so is give you a glimpse as to how one can actually commercialize the innovation and invention that comes out of this. So to set the stage, I think it's appropriate to reflect on the incredible economic impact Stanford has had on California. I mean, these numbers are quite astounding when you think about it. To me, one of the most salient facts here is that almost 40% of Stanford founders located their companies within 60 miles of the university, an hour away. This has created an extremely dense and concentrated aggregation of talent and entrepreneurship and innovation. And you had the subsidiary things coming in like funding and partners and other things like that. So it is this that I think is one of the defining features of Silicon Valley and has contributed to successive waves of innovation and technological evolution out here and revolution out here in the Valley. The same is true for energy. I mean, if you look at the sustainable energy landscape, here are some sustainable energy companies that have either come out of Stanford or have strong links to Stanford. And coupled with those that don't have Stanford connections, you can imagine that here's this very large ecosystem that is developing, a supportive ecosystem in which new companies can kind of swim in this kind of sea that they create. The companies listed along the top are the ones that have come out of the TomCat program, 3 of which you're going to hear about today. So a few words about the Tomcat Center. This was founded in 2009 with a generous gift from Tom Starr and Kat Taylor. And the mission of the center is to support sustainable energy research, education, outreach, and innovation transfer. And when we look at sustainable energy, we take a very broad view of it. I mean, we have a very loose interpretation of it. So, of course, it includes things like energy generation, transmission, storage, management, efficiency, transportation, things like that. But we're particularly interested in the intersection of energy with food, water, and the environment. I mean, because energy is sort of pervasive in all of these, and this is of very great interest to us. And it is reflected in the kinds of projects that we support. Now, we have a sister organization. We're more technology focused. We have a sister organization who got the last names. It's called the Starr Taylor Center, and it works out of the law school, and they're predominantly focused on policy. We work reasonably closely together, given how multidisciplinary Stanford is. So the Innovation Transfer Program that I'd like to talk about is a very somewhat unique and very immersive experiential learning experience. It really gives people first-hand tools and experience in commercializing a very early stage technology out of the university. And we launched the program in the fall of 2013. We've given out about $1.6 million in funding to these teams, to 18 teams to date. There's been about 50 students who have gone through the program now in this short period of time. In this time, they've raised something like $15.5 million in follow-on funding. So this has been quite impressive. And some of the other accomplishments of these student-led teams are 1 acquisition, 3 very competitive Sunshot Awards from the DOE, 2 SBIR awards, 1 ARPA-E grant, 5 teams either who have been or are at StartX, the student accelerator, which I'm sure you'll hear about, and 2 teams who are at the very competitive DOE accelerator, the Cyclotron Road Accelerator. The grants, the innovation transfer grants that we offer to students are primarily intended to help them build prototypes. I mean, these are commercial-ready prototypes, refine business plans, conduct customer trials, pull together teams, really get to the point where they can walk into a VC meeting, for example, with the tools required to give a compelling presentation. Validation of their business proposition, validation of their technology. This is really what we strive for. We provide them with the services of some volunteer mentors and advisors, many of them serial entrepreneurs or people who have been in the space a long time, and they can provide easy access and introductions to potential strategic partners or customers or investors for that matter. So it's a very comprehensive program. We don't run any entrepreneurship courses per se, but we capitalize opportunistically on the huge network of entrepreneurship programs that are available on campus. The ones that have been particularly useful to our teams are the Center for Entrepreneurial Studies out at the GSB, particularly the venture studios, also the D School, where they have some very valuable classes, some of them project-based. The joint MS program for the MBAs, JDs, and MDs is another excellent place where projects emerge. We've actually funded 4 of them out of that program. And then, of course, StartX. I'd encourage you to go to the Stanford Entrepreneurship Network website, where you can get a lot of information, perhaps more than you want, about all the resources on campus. I think you'll be kind of surprised when you see how much there is. So looking at the 50 students that we have, you can see about a quarter of them are MBAs, and the rest are from the engineering and sciences. Mostly graduate students, though we have a smattering of undergraduates, 5 of them. I should say that the company that was acquired was founded by 3 20-year-olds, so you know, they're not slackers by any means. But it is quite a broad cross-section with people from multiple schools. So the Tomcat Center, which kind of coordinates this innovation transfer in the sustainable energy area, is a very small, lean operation. We kind of run it as like a startup. We move on a dime. The faculty director is Professor Stacy Bent, who will be talking to you at 10 o'clock. Myself and Donika Sarlia at the back over there. She's the program manager who does a lot of the heavy lifting, runs a bunch of programs, including a very popular summer internship program at energy startup companies. I'd encourage you also to go check out our website, because there's a whole bunch of information and description about our programs and other resources that are available. So what I'd like to do now is hand the floor over to John Basbigill. You're going to have three of our founders, 3 people who have gone through our program, present to you. And John's going to be the first one. All 3 of them are PhD engineers of one description or the other. And Bryce has an MBA from the business school as well. So right now, thank you very much, and please welcome John Basbigill.
Talking about your life, your history, your research here at Stanford, and the commercialization of that research in 10 minutes is a bit daunting, but I will do my best. And if anybody has any follow-up questions, I'm happy to talk to people after the event. So my company that I'm working on is called Spectrum, and it provides energy analysis software for the architecture industry. Before I go into details on the company, I'll just give you a little overview of my background. So these are pictures of my hometown growing up. I grew up next to a forest preserve, and in fact, my first summer job on the upper right, that was my crew, when I was 19 years old, involved doing conservation work in this forest preserve. Built some bridges, maintained trails, and this is a picture of that forest preserve. I show this to kind of conceal kind of the thread that I've had through my life of kind of interest in and respect for the environment, the outdoors, something I've been kind of passionate about my whole life. I'm not, I would say, a tree hugger by any means, but the environment is something that's important to me. So moving on to my academic history, kind of moved around the country a little bit in terms of the different degrees. The blue are the states that I visited. Went to a wedding in Texas last weekend, so can cross that one off the list. But anyway, I studied engineering at Harvard, mechanical engineering, a little known program. There were 3 of us, so moved on to my master's at USC. I studied building science in the School of Architecture. It was a research-based program, which I loved and kind of fed my interest in doing more research. So that's what brought me to Stanford in 2009, did my PhD in civil and environmental engineering, and I focused on lifecycle assessment of buildings and conceptual design of buildings. Last year, I was in the first cohort at Cornell Tech. Cornell Tech is a new partnership between Cornell University and the Technion in Israel. They won the bid to develop Roosevelt Island in New York City. And 2014 was their inaugural year for postdocs to commercialize their PhD research. So I was there last year. They gave an initial investment in my company. And then this year, Stanford has funded me. So I'm back here doing a second postdoc in civil environmental engineering. A little more about me globally. Again, the blue are the countries that I've visited. So a little fun mixed in with some experiences that tie into what I'm doing now. So just some travel pictures. I was in a Bollywood film in Singapore airport as an extra. I wasn't cast. I was just sitting there waiting for my flight, and they just said, "Would you mind us filming you?" Anyway, the pictures on the right are all in Thailand and Laos. So I worked for a company called Rustic Pathways for 7 years on and off, running adventure travel trips, but also I was their sustainable development manager, building some really cool community service bases. You can see here, the setting is just spectacular. It's on the border between Burma and Thailand. So anyway, these were some of the structures that I helped design for this site. Really cool experience, and obviously, again, ties into this theme of the environment and even the research that I did at Stanford, which again focused on life cycle assessment. So if you're not familiar, life cycle assessment is a accounting method for looking holistically at the impacts of a product, a process, or in my case, a building. So we're looking at these, you want to look at upstream impacts of materials, where they came from, raw material acquisition, processing and manufacturing those materials, packaging them, distributing them, transporting to the sites. And then the operational phase, the usage is very important. And then finally, end-of-life scenarios, that's recycling or disposing. This is a general framework that can be applied to all sorts of things. And then specifically to buildings, again, you have the upstream impacts for the materials. And then the usage is a critical phase there for operating the systems of the building. That's heating, cooling, lighting, water, plug loads, etc. So this is the framework that I used for my research here. Another piece of my research was integrating computational analysis. So the problem right now in the architecture industry is that architects don't have tools to evaluate lots of options in buildings. So it's a very uncoordinated and kind of slow process in that they manually have to iterate and evaluate one design at a time. So over the course of a month or two, typically an architect will only evaluate 3 options. They'll get very thorough analyses, but the problem is that they're not really seeing the big picture of all the different options that they could consider. So a big part of my research here was integrating computational processes so that architects can look at lots of other options very quickly. This is the kind of the computational framework I used in my research. So the first piece is what's called building information modeling. That's kind of CAD, computer-aided design 2.0. It's come along in the last 10 to 15 years, which allows architects to more intelligently design in 3 dimensions and assign information like materials and the site conditions to their model. What I then did was integrate all sorts of analyses programs, embodied impact, cost, operational energy, into this computational framework, which allows architects to get feedback very quickly on lots of options. A little demo here for the prototype that we're working on right now. Oh, and I just want to mention too, this was the sort of point of departure between my research at Stanford and the commercialization of that. So this is the framework that I've been building off of in the last 18 months now. The demo here, so the program is a plugin to building information modeling software. The initial program we're working with is called Rhino. That's the gray design environment in the back. And then we overlay a plugin on top of that. It takes 3 inputs: the location of the project, the size of the building, and the type of the building. Optionally, you can add in more information if you know it, but this is typically an early stage of the project when an architect doesn't know much. So this is the real power of our tool that we're building, is that we're enabling architects to get a lot of quantitative information very quickly, given very few inputs. The next step is that we're building a processor in the cloud to extract information from the building information model, then generate lots of options very quickly, and compute cost and energy use impact for each of those options. So you can see here, things are changing: the height, the glazing ratio, the shape of the building, and cost and carbon performance are being calculated for each of those options very quickly in about 5 seconds for 20,000. Coming back down from the cloud, we then deliver a front-end piece showing the full results on carbon and cost performance. And the real power of this is that an architect can see very quickly the relationship between, on the left, the input parameters, and on the right, their performance. And so, for example, this is useful for the architecture industry because there's a lot of energy codes and green building rating specifications that are very challenging to meet, and we can show how their design decisions can relate to those energy codes. So that's a little bit about my company. Been working on this for 20 months now in total, and we've developed a lot of relationships with different partners over that time. So TomKat has been a generous funding source that we're really grateful to have to really make a push for commercialization. SIFE is the department that I'm based in civil and environmental engineering. I'll just point out a couple of these. So BASES, as Brian mentioned, is the on-campus student organization. They have a contest in the spring every year for who has kind of the best entrepreneurship ideas. It's a really cool contest. I'd encourage everybody to get involved if you're interested in this. And it's all sorts of ideas, not just energy related. So we participated in that last May and got 2nd place. And yeah, there's a few more contests. And then finally, just the team that I'm working with right now. Sergio is a PhD here in civil environmental engineering with a background in energy modeling of buildings. And Eldar is a CS full stack developer. So a lot of technical ingenuity in the team right now. And that's all I had.
All right, thank you. So my name is Itasha Cave, and I'm the Chief Science Officer of Opus 12. And we like to say that we're converting waste CO2 into wealth. And so before I talk about the technology and the value proposition, I want to first talk about the team, because that tells a story of how we came together. So the founding team consists of Kendra Kuhl, myself, and Nicholas Flanders, shown here. And we all are Stanford graduates. Kendra and I worked together in a lab here at Stanford in the chemical engineering department for about 5 to 6 years. And we worked on similar technology to what we're doing in our company. Nicholas Flanders got his MBA here and is still working in the IPERT program to get a master's of engineering. And we found Nicholas through a networking event here on campus. It was a clean tech networking event in the business school, and we talked to him and told him about our idea, and he joined the team. So that's something to keep in mind as you join these clean tech events, to be looking out for maybe future co-founders as you guys are going throughout this week or any other events that you attend, is that there are people out there with common interests and that want to do very similar things, and you guys can come together and actually make something out of that. So the 3 of us worked together in our free time for about a year while I was finishing my PhD, and Kendra had a postdoc at SLAC, and Nicholas was also finishing his MBA. And as we were working, we were getting the business model together, we were refining the idea, and we eventually got into, well, we got a TomKat grant, which was really helpful, and then we got into an accelerator program at the Lawrence Berkeley National Lab. The accelerator gave us seed funding, so we got about $500,000 over 2 years, which allowed us to hire our first employee, which is shown here, which is George. George has an abundance of experience in the area that we need. So with this money, we were able to hire people. We have lab space. We're able to develop a prototype. So with TomKat as well as this accelerator, we've been able to really grow out our team and make this a reality. So we have a team of advisors that have been really helpful. So one is my former PhD advisor, Tom Bartholomeusz. So he's been really helpful and really supportive of us with this endeavor. And then Kathy Ayers, who's a development partner, she's working with us to develop the technology so we can bring it to market much faster. We're also working with 2 professors, one at Cal and one at the University of Texas at Austin. So it's been a really great support system that we were able to put together because we have this idea and this technology that we're driving forth. So the question now is, well, what is our technology? So at Opus 12, we like to ask the question of, what if carbon dioxide emissions never reach the air? What if instead we could transform them into high-value, useful products? And so that's what our technology does. Our technology uses electricity, the same electricity used in your home to charge your iPhone, to run your appliances. We use that electricity to break down carbon dioxide and water over a metal catalyst. And when you do so, you break the CO2 and water into smaller bits and pieces. And then if you have the right metal catalyst, the right amount of electricity, and the right conditions, those bits and pieces will form new molecules. And in fact, in my research here at during my PhD at Stanford, we identified 16 different new molecules that we're able to make using CO2, water, electricity over a metal catalyst. Now, these 16 products are currently used in the world today. And in fact, the top 8 of them represent a $400 billion market. So these are products that are currently sourced from petroleum that we use to make our lives comfortable. So if instead we could make these products from carbon dioxide and water, we could have a way to make greener chemicals to replace the chemicals we're currently getting from petroleum. So our initial customers and our initial chemical that we're looking at is ethanol, shown here. And our initial customers would be for current fuel producers. So there are 3 types of fuel producers that we've identified that this would be a huge value proposition for. So one would be oil refineries. So oil refineries right now make hydrogen. That hydrogen is often used in agricultural for fertilizer. But in the production of making hydrogen, they release CO2. There's also corn ethanol producers. So 10% of what you put in your car is ethanol. That ethanol comes from corn ethanol producers. And in the production of making corn ethanol, for every ton of ethanol they make, they emit a ton of CO2. And there's also natural gas fields. So in the process of finding natural gas, some CO2 is released. We can take that CO2 from all 3 of these players, and we can make more ethanol for them. And that ethanol can be used to displace gasoline, so that at some point we would have more ethanol being blended in the car that would have been CO2 that would have been emitted into the atmosphere. And from these 3 players, we've identified that there's 100 million tons of carbon dioxide being released. And if we converted that into ethanol, it would create a multi-billion-dollar revenue stream for these particular customers. So just a quick overview of our technology. So again, we're taking the CO2, water, and electricity. We're using our reactor, and here's an image of our reactor. So this is a production scale reactor. So this is basically the size of a check-in suitcase. So you can imagine wheeling this guy around, and that is what will take the CO2, water, and electricity and make the ethanol for us. And then we would take the ethanol and use the existing supply chain and get that ethanol to market. So we've done some cost models of how much would this cost, and so the main driving force is the electricity. We ideally would love to use renewable electricity because not only do we predict that there'll be an emerging market of surplus intermittent electricity, but that it'll be much cheaper than what we're getting on the grid, because you have solar that, when the sun is out, you have solar that's solar electricity that's being produced. There's not always a demand for it, so that electricity we can use, that surplus electricity we can use to make these liquid fuels. And so you can see here, depending on mainly the cost of the electricity and the cost of the CO2 that we're producing, we can make ethanol, all the way down to 87 cents, which is using wind turbines at night, which is available in Texas right now. So these are actual costs that we've gotten from consumers in Texas. So So just a couple of our innovations that we've made. So what we've done, in working on our prototype, we've made this initial smaller reactor to prove out idea. And once we have a reactor that meets the performance points that we've determined that we needed to go to market, we'll then integrate that into our larger industrial scale reactor, which again is the size of a check-in suitcase. That reactor we envision putting into shipping containers, and literally you would drive this reactor out to your customer, and they would be able to make ethanol on site from CO2, and ideally surplus renewable electricity. So just finally want to leave you with this quote from Mr. Fuller, which is, "Pollution is nothing but the resources we are not harvesting. We allow them to disperse because we've been ignorant of their value." And so at Opus 12, we hope to someday take right now what we're throwing away, which is carbon dioxide, and create higher value out of it. So I'll be around at the end to answer any questions if you guys want to know more about our journey to creating this company or more about the technology itself. I'd be more than happy to answer any questions.
Okay, great. Last on the list, but not last in your hearts, I hope. I'm Bryce Meredith. I'm one of the founders. Oh, we're not up there yet. I'm one of the founders of a company called Citrine Informatics. We got our start here at Stanford as well. And in true Stanford fashion, taking a software approach to a physical world, manufacturing world problem, which is that we're bringing large-scale data collection and analytics to the materials and chemical industries. We're not an energy company per se, but it so happens, as many of you might know, that very many energy problems and sustainability problems are materials problems at their core, and we can make those problems much less serious. And in fact, a lot of the work we're doing, you'll see this throughout my slides here, a lot of the work we're doing is in energy specifically. And our project here, our TomKat project here, was actually in catalysis, which we've heard some about already. So a little bit more about the company. Our mission statement sounds not unlike Google's. We unlock new and hidden insights from humanity's materials data. We don't care about data on the web in general. We only care about materials and chemical data. And our goal is to be the best in the world at harvesting it at a very large scale from very many different sources, and then using state-of-the-art machine learning techniques to extract value from it and deliver insights from that to major materials companies, the Dows and DuPonts and Alcoas of the world. So a little bit about our team. This is actually an out-of-date photo. There's more of us now. So we're taking a new team photo in a couple weeks. There's 3 founders of the company. We're all material scientists by training. We all have advanced degrees in materials. I don't know if there's any, hopefully there's some MSc folks here in the audience today. And we also, as you would expect, since our company sits right at the confluence of material science and computer science, we also all have simulation and modeling or formal software backgrounds. And there's a deep Stanford connection, obviously. So I did my undergrad at Stanford 07, material science and German studies, but material science is what pays the bills now. And I came back for a victory lap to do an MBA at the GSB. And in between, I actually I did my PhD at Northwestern, so I've been in school for a really long time. And I saw, John, are you from the Chicago area? Yeah, I love it. It's great. You should all visit. A lot of people in California have never been to Chicago. It's awesome. And my co-founder, Greg, who's on the far left there, is also a Stanford MBA. We met at the GSB. There are not many material scientists at the GSB, so we got to know each other pretty quickly. And then I recently became consulting faculty in the materials department. So we have very deep connections here to this place. And unfortunately, I have to admit this, given the audience here, we have one very proud Cal Bear on the team. The third co-founder, Kyle, went to Cal. And if you're wondering, yes, we are doing a team tailgate for big game. So it could get ugly. We'll see. Especially given that Northwestern game, I don't know how I feel about our chances. Cal's not as much of a easy win as it used to be. So here's what are sort of the value props that our software platform delivers to a typical customer, which are not only big materials companies, but also companies that need advanced materials for their products, like Samsung, Apple, General Motors, Boeing, companies like that. Actually, we talk to them a lot too. One is kind of the most obvious. Let's use large-scale data, patterns in these huge materials and chemical data sets to predictively guide R&D. as maybe an alternative to traditional simulation and modeling. We can also optimize manufacturing and improve yield, diagnose problems. We can do real-time analytics of inline characterization data of materials that are going through the manufacturing environment. And interestingly, we can also help predictively guide sales. So some major chemical companies, for example, are maybe a little less interested in inventing new polymers, as exciting as that is maybe to all of us who are scientists, and are more interested in selling more of the polymers they already make. So we have technology that can do that as well. Here's a schematic of what we do for these, what our platform does for these different customers. We view the world as consisting of very many different sources that might teach an algorithm about how materials behave. And this is just a subset of them. So most obvious to the people in this room would be papers and patents. We actually have algorithms that will go through papers and strip out information from the figures, the tables, the text, and so forth. Patents, similarly. We also integrate information about commercial products, internal R&D data, existing databases. Our platform can bring all this data together and use algorithms to analyze it for our customers. So, of course, the goal of this always is to deliver some kind of actionable insight based on analyzing all this data in the aggregate, which is something that none of these companies can really do today. And we've been finding out they've been trying to build these sorts of solutions in-house and have been having trouble because they're not IT companies. So what does it mean to do machine learning for materials? Actually, our first demonstration project was in the area of thermoelectrics, which is energy. And I guess Arun either spoke or is speaking. He's a world leader in this area. And actually, he was part of our diligence process that our investors put us through, which is getting grilled about thermoelectrics by Arun is an intense experience. Let's put it at that, leave it at that. But our goal was we simulated in collaboration with some academic groups. We simulated a huge amount of data about how different thermoelectric materials behave, the key performance parameters like the resistivity, the thermal conductivity, the Seebeck coefficient, and we built predictive models that can very accurately assess whether any given chemical compound might be an interesting thermoelectric. So this screenshot over here is a graphical interface to these models. We don't want people to have computer science degrees or machine learning backgrounds to understand what's going on. This is intended for material scientists and chemists. And those bars indicate how likely a given material is to have the right values of those different properties I mentioned. And we can also do sort of brute force screening through huge regions of composition space for new interesting materials. We did a brute force through every ternary system. That's one slice out of 100,000 ternaries. And we generated these heat maps that then guided our collaborators to the synthesis of some new materials. And in fact, this worked. The proof always has to be in the pudding. If anyone else here does computational modeling, you'll know that one of the scariest things to do is make a prediction, because you could be wrong. But luckily we were right. So this is a schematic illustrating sort of the known universe of thermoelectric compounds. This was what was in our training database for our algorithms. Each dot on here is a distinct compound. The materials are located according to the weighted average positions of the elements in the compound. So boron nitride, for example, would sit right on top of carbon, halfway between boron and nitrogen. What you see is that known thermoelectric space is clustered over here. That's what the oval indicates to you. It's chemically, they're chemically relatively homogeneous. That's what this illustration shows you. And so the question we asked with our collaborators is, how would you break outside of this usual suspect search space to find needles in a haystack that are outside of that? And that's, of course, very, very difficult to do, certainly with traditional experimentation, even high throughput. It's also difficult to do with traditional physics-based models. But we actually used our very, very fast machine learning models to point our collaborators towards a rare earth ternary alloy out there, which, if you just look at its chemical formula, it doesn't look like it should be a decent thermoelectric at all. But it actually performs similarly to silicon, which is being commercialized as a thermoelectric today. So it was a case where the machine learning models were able to deliver a result that was not necessarily chemically intuitive, but turned out to work in the laboratory, which of course is sort of the holy grail of what we're trying to do, helping people augment their own intuition as chemists or material scientists to make new discoveries. And a big theme behind what we do is filling in gaps in knowledge. So this is, I won't spend too much time on this, but this is sort of the sales-oriented side of what we do. But product designers who are selecting materials will specify ranges of properties that they want. Those properties aren't always measured. And in the cases that they're not, we can actually fill in the gaps predictively. That's what these little calculator icons are. So if you're a product designer at Ford and you're selecting a new alloy, you don't need to make all these measurements yourself. We can predict them for you. So that's a little bit about the product, but I want to say a few more words about the start of the company and our team. We got our start here at Stanford, as I mentioned. We were born at a mediocre burger joint. This is the Islands Burger in Cupertino, if anyone's ever been there. And the genesis of the company was my co-founder, Greg, a fellow GSBer, actually had a materials idea that he wanted to pitch to Apple. And I know some friends of mine are in materials R&D at Apple. And I said, okay, I can get you in front of some of these guys and you can pitch your idea to them. And over lunch at Islands, and that's why we were in Cupertino, we started talking about my research background, which was materials informatics, machine learning applied to materials data. Greg started talking about his background, which was running a reactor growing gallium nitride and generating a huge amount of reactor log data and not knowing how to analyze it. And so even though the point of the lunch was to sell something to Apple, we ended up talking more about how could we use data analytics to really change the game in the materials industry, and that was where the company was born. Our first funding came from TomKat, so I just want to make sure to acknowledge, of course, all of us are TomKat teams, but I want to acknowledge Brian, Donica, and Stacy, who I can really say we would not be where we are today if it weren't for TomKat support for many reasons. Not only because they were the first funding that was provided to our company, which is a huge sort of de-risking moment in the eyes of federal granting agencies or certainly private investors, but also because once you join the TomKat ecosystem or the TomKat family, they're always looking out for you. So they've been continually introducing us to people. They sponsored our participation in the Stanford Career Fair. They sponsored an intern for us over the summer. And we've been benefiting in countless ways from our connection with them. So I'm out of time. The last thing I would say is there's lots of resources here for you as a Stanford student interested in entrepreneurship. The Citrine team did Launchpad and Startup Garage. Of course, you may have heard of Lean Launchpad too. That's another option. And we were also in StartX. So if anyone has questions about any of these classes or StartX or, of course, anything else about the Citrine journey or TomKat, I'd be happy to answer them afterwards. Thanks.
Okay, we have time, a very short time for a few questions. Please feel free to ask any questions of the three speakers that you have heard. You guys want to stand up here? And don't be shy. At the back. Should I take that?
So you just showed the pie chart of the students from each school who are in the program. What percentage of those teams are cross-functional or across the schools? Or are they typically teams, two GSBers like within the team? Or do you see people partnering across different programs?
They're quite diverse. So some of the teams may be fairly homogeneous, but I would say of those 18 teams, probably 3/4 of them are quite diverse. They have people from multiple schools, CS, engineering, the business school. So it wouldn't be like 3 GSP people on one team, though there are a few teams that may have 2 of them. So the teams are pretty diverse. And as Etosha said, there are some really good events, networking events that you can attend that bring people together, where you can get up and talk about your ideas and get other interested parties to join with you.
So I have a question for each one of you. The question is, what was the hardest point in your entrepreneurial journey, especially like transitioning from hardcore being a scientist and doing research in a lab to an entrepreneurial path?
I guess I can start. This won't be so much about commercializing work right out of a lab because our path started over at the business school, but for us, the hardest part was demonstrating product market fit. So that's a term maybe a lot of you have heard tossed around. But basically, that's proving that the dogs want to eat the dog food. And in a business like ours, which is not sort of very intuitive to a lot of investors, a lot of them aren't thinking about what software needs does Corning have? Like, that's not something that a lot of people worry about in Silicon Valley. There was a lot of question about, is this a little lifestyle business, or could this be a billion-dollar company? There was no calibration for a lot of investors around here, and so we had to go out there and prove that these big companies will pay real money. We had to go sign up GM and Boeing, companies like that, to prove that there is something there.
Okay, I would say our hardest challenge was finding funding, which is, I think Bryce said it, the TomCat grant, which is really huge to give us that first initial credibility. When we were starting out, I remember I very naively thought, oh, we're a bunch of Stanford graduate students. People give us money because they know that we have good ideas and we'll get stuff done, and we've been working on this for so long. And
We're in computer science.
yeah, exactly. Yeah, if you're in computer science, that might be the case. But for our technology, like, we needed to make a prototype, and the prototype costs a lot of money because we need very expensive equipment to make the prototype, and then we need to test it, and we need to iterate. And so no one would give us money until we had a prototype, and we couldn't afford one on our own. So we were just kind of, this chicken and the egg problem. So by getting into the accelerator and having this initial amount of seed funding, we're now able to build our prototype. And then when we're ready, we can then go and approach VCs and get the larger scale-up amount of funding. But I mean, for us, it's just been a complete, wake-up call of we needed to go out and raise funds, and we've done that through grants and applying through business plan competitions, and that's actually been, we found out now, is the way to go. I mean, getting VC money too early can be kind of detrimental to clean tech companies, so it's something you want to watch out for if you're going to do a hardware-based technology. It's like the longest you can prolong, getting that VC funding, the better off you'll be. So we're in a really good position now that we haven't taken any dilutive funding, and we're able to build our prototype and get ready for the moment when we do need to take on funding.
I would say for me, the hardest part of my journey was the first 6 months after I graduated from here. Like many of us standing up here, I'd been in school forever and hadn't really, I mean, you saw my slides of like the work experience I did, which was very hugely impactful, I thought, but not very, I guess, like corporate, very business, I didn't learn much about business while I was doing that. And to have to come down out of academia and be thrown into the streets of New York City as my kind of first real corporate experience was a huge learning experience. Talking with customers, interacting with investors was, eye-opening, but very challenging. So that's, yeah, it was a good learning experience. It was very difficult, but that was the hardest part for me.
Okay, we have time for one more question, then you can talk to the speakers outside while you're
So this is for Opus 12, but if you guys have anything to say about this, we'd love it as well. So in your case, you had the technical knowledge, you and your partner, and the idea as well. So there are a lot of smart business guys around. I just want to know why you picked particularly that one out of everyone else, and then and then when you got to later stages, obviously you don't need to go into specifics, but when it comes to ownership structure, value assigning in terms of who's going to do which role, that kind of thing, I'd love to know more about how you guys actually got onto that level.
Okay, that is a great question because I have worked with many MBA students, and no offense to any MBA students in the room, but it's not every MBA student is naturally fit for a startup. Sometimes they may be good for a larger company, and you really want to pick your teammates really, really well. Okay, so the question is, like, why do we pick Nicholas? Okay, so first of all, Nicholas is more than an MBA student. He is actually getting a master's here at Stanford in like industrial engineering. So he can understand the technology very quickly. In fact, he got a bachelor's in math, so he's very sharp. He understands what we're doing, on a high level. He can't be in the lab and build stuff, but he understands it very well. And he also can do a lot of our techno-economic analysis. So through his master's here, and plus his former role as a consultant, as a McKinsey consultant, he worked in a clean tech practice where they looked at very, big problems around clean tech and clean energy. So he has that background of doing, spreadsheets and doing analysis. And one thing I found as like just a tip, like MBA students who are former consultants I've had a phenomenal experience with them. They tend to be hard workers. They're used to working with a team. They're used to putting together large sets of data and looking at data, and tend to have somewhat of a technical background. So as sort of an initial filter, if you find an MBA student who's a former consultant, they could be a really good fit. But even with Nicholas's background, we still kind of had a bit of a trial period. I mean, for a year, we were working where we didn't have a company. The three of us were working in our free time. We had full-time jobs. I was finishing my PhD. Nicholas was finishing his MBA. But we worked on business plan competitions. In fact, Flow, which was mentioned in previous presentations, was a competition we first worked on. And so we really got to see how we could work together as a team. And we put together a business model, and we were presenting that, and we got to see how involved Nicholas was with us. And so that was like a huge kind of validation for us to see that he could, work well together. He could bring value to what we were doing, and he's been just phenomenal ever since then. So definitely, if you're working with anybody, even if they're an engineering person, like, try to get some way to work with them in a business plan competition to see how you guys work together as a team. If they're a former consultant, might be a good sign that they're, good, hardworking, could be a good fit. Was that all your questions?
Please give our speakers a